So today we will be talking about a new algorithmic technique, which is dynamic programming. So we will discuss two problems. One is a relatively simple problem, which is the Fibonacci number calculation, which should be familiar for most of you. This problem illustrates the difference between the dynamic programming approach and other approaches. So everyone is familiar with Fibonacci numbers. Fibonacci of 0 equals 0. Fibonacci of 1 equals 1. Fibonacci of 2 equals Fibonacci of 0 plus Fibonacci of 1. And in general, Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay? Now, and many of you have probably written a recursive algorithm for computing Fibonacci numbers. Long, let's say n is going to return, or for the base cases, if n equals 0 or n equals 1, return n, else return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this is a recursive algorithm for computing Fibonacci numbers. Now, if we try to analyze the asymptotic complexity or analyze the behavior of this algorithm, we'll see something like this. Fibonacci of Fibonacci of n is going to call Fibonacci of n minus 1 and Fibonacci of n minus 2. And Fibonacci of n minus 1 is going to call Fibonacci of n minus 2 and Fibonacci of n minus 3. And this is going to call Fibonacci of n minus 3 and Fibonacci of n minus 4. And this is going to call Fibonacci of n minus 3 and Fibonacci of n minus 4. And we will continue until we get to Fibonacci of 0 and Fibonacci of 1, which are the base cases. Now, what's the running time of this algorithm based on this tree? Based on this tree, what's the running time of the algorithm? So, what's the height of this tree? Yeah, so the height of this tree is going to be theta of n, because you will get, you go from n all the way to 1 or 0. So the height of this theta of n. Now, if there is a tree with height theta of n, how many nodes will the tree have? What's the mathematical relation between the number of nodes in a tree and the height of the tree? Yeah, it's exponential, right? So assuming that it's a complete binary tree, it's not complete. This is not complete because some end at 1, some end at 0. But assuming that it's for a good approximation, assuming that it's a complete binary tree, if the depth or the height is n, then we have 2 n plus 1 minus 1 nodes. So remember this formula when we analyzed complete binary trees. So in summary, the relation between the number of nodes in a tree and the height of the tree is exponential. So the number of nodes is an exponential function of the height, or the height is a logarithmic function of the number of nodes. So here, what's our input size? Our input size is n, which is the height of the tree. So our input size is n, which means that the number of nodes is going to be exponential. So this is going to be an exponential algorithm. So if you try to compute this, if you write this innocent function, this function that looks very innocent, and if you write it and you give it sufficiently large values of n, and based on the calculations that we did earlier this semester, you should know what is large and what is small for an exponential. So if you do 50, for example, that's large. So 50 is not going to finish. It's going to take forever. Okay. Now, so we know that it's exponential. But now let's try to think about the algorithm and see why it resulted in such an huge running time. Where is the problem in this algorithm?
A lot of duplication.
Yeah, exactly. It keeps solving the same subproblems over and over. So, for example, this is a big problem that got divided into two subproblems: the subproblem of finding n-1 and the subproblem of finding n-2. But then we keep encountering the same subproblem multiple times. For example, n-2. So here's n-2, and here's another n-2. If you look at n-3, here is an n-3, and this is another n-3, and this is a third n-3. So the problem here is overlapping subproblems. So in fact, this problem has the optimal substructure. The problem itself has the optimal substructure property in the sense that you can use solutions to the subproblems and build solutions to the original problem. Of course, remember that this is not an optimization problem at all. So it has the optimal substructure, but this is not an optimization problem at all. This is just a computational problem. We will see the 0-1 knapsack, which is an optimization problem, in a minute. But the problem with the algorithm is that the subproblem is encountered multiple times and is solved multiple times. So there is a lot of duplication here. Now, how can we avoid this? We can avoid this by solving each subproblem only once. So what if we just, instead of taking a top-down approach to the problem, instead of taking a top-down approach, starting with the big problem and dividing that problem to smaller subproblems, what if we start from the bottom of the tree and solve the smallest problems, the base sizes first, then use the solutions to the base problems to build solutions to bigger problems, and so on. We go in a bottom-up approach as opposed to a top-down approach. This can be easily done for the Fibonacci as follows. So we can write, well, instead of this, we can write Fibonacci of long n. So we can create an array A of size n plus 1. Why n plus 1? Because this is because we need to go from 0, 1, 2 through n. So we need n plus 1. So we can just solve this base problem. Solution is 0. This base problem, solution is 1. Then given these two solutions, we can solve this problem. So it's just the sum of 0 and 1, which is 1. Then this subproblem is the sum of the solutions to 1 and 2. And that gives us 2. And for 4, we just add 1 and 2 and get 3. So this looks easy. So instead of starting with the big problem and going top down, we're going bottom up by solving the basic or the base sizes, the problems with the base sizes first, then using these solutions to these small problems to build solutions to bigger problems. And so we keep going until we get to the whole problem of size n. Yeah.
So this means we're not using recursion? Is that what this means?
Well, it's not just a matter of recursion versus non-recursion. Here, using recursion resulted in these overlapping subproblems, but it's not, it's not anything that you can do with recursion, you can do it without recursion. So you can you can implement the same approach without recursion. But the idea here is the is the algorithmic technique, which is instead of thinking top down, think bottom up. Solve the smaller problems first, and then use the solutions to the smaller subproblems to build solutions to the bigger problems. But yes, recursion, when you use recursion, that will tend to give you a top-down approach to the problem. And in this case, it gave you all of these overlapping subproblems. So here, if we were to just try to create an array A of size n plus 1, and then set A of 0 to 0, A of 1 to 1, and then go for I equals 2, for I equals 2 to n. A of I equals what? A of I equals? I minus 1 plus A of I minus 2. Okay? And then what should we return? What should we return? A of n. Yeah, we return A of n. Okay. So now, by doing this, we are solving the smaller problems, and we are storing the solutions to the smaller problems in a table. This array, you can think of this array as a table. So we're storing the solutions to the smaller subproblems, and whenever you need a solution to a subproblem, instead of recomputing it, you just look it up in the table. Solve subproblems, store the solutions to the subproblems in a table, and instead of recomputing a solution to a subproblem, you just look it up in the table and use it. And if you do that in the right order, you will get this algorithm. So the running time of this algorithm is exponential. This is an exponential algorithm, while this, what's the running time of this?
N.
Yeah, this is just theta of n. So we managed to replace this exponential algorithm with a linear time algorithm. So this is very much as slow as it can get, and this is very much as fast as it can get. So this is linear, one of the fastest, and this is exponential, one of the slowest algorithms. And we managed to do this by looking at the problem bottom up, solving smaller subproblems, storing solutions in a table, and reusing them. So this is the idea of dynamic programming. Now, let's apply this to the 0-1 knapsack problem. The 0-1 knapsack problem is a problem that we could not solve using greedy algorithms. So let's now see how we can solve it using dynamic programming. how can we use the same idea to solve the 0-1 knapsack problem? Well, let's first look at the example that we will be using. This is the example. 2 kilogram and $3. 3 kilograms and $4. 5 kilograms and $6. And then the knapsack has a capacity C equals, well, let's big C equals 8 kilograms. Okay, so this is the example that we will be using. Now, how can we apply dynamic programming to this? The idea is to start with some base case that we can solve easily. What is that base case? That base case could be, for example, having item 2, item 3. What if you have only one item? So that's a base case. I only have item 1. Only item 1, and I have a capacity and C equals 1. If you have item 1 and a capacity of 1, what would the solution be? 0, because item 1 has a weight of 2 kilograms, so I will not be able to take it. So it's just the solution is 0. So this looks trivial, but as we will see later in this lecture, we will be able to use these trivial solutions to these easy subproblems to build solutions to bigger subproblems, and we will keep computing solutions to bigger and bigger subproblems until we eventually build the solution to the whole problem. So it's even though we will start with trivial solutions to trivial base cases, we will end up building a solution to the big problem. Now, we can increase the size of the subproblem. Now remember that now we are thinking bottom up. So we are starting with smaller subproblems and we are building bigger. Instead of starting with a big problem and creating smaller problems, now we're starting with smaller problems and making them bigger and bigger. Now, how can we make this bigger? This problem has 2 dimensions. It has the item, the number of items, and it has the capacity. So we can grow the problem in either dimension. We can grow it by either including more items or by increasing the capacity. So let's try to grow it by increasing the capacity. So what if we have item 1 only and we have a capacity of 2? Now, with a capacity of 2 and item 1 only, item 1 is going to fit in this knapsack, and it's going to give us a value of 3. Okay? So we can keep growing the problem by increasing the capacity. On the other dimension, we can grow the problem by adding more items. So we can look, for example, at item 1 and item 2 and the capacity of 1. Okay? What's the solution in this case? 0. But if C equals 1, if C equals 2, with the same items, item 1 and 2, then the solution is going to be 3, and so forth. Now eventually we will draw a table that will show all the subproblems. We will show, we'll start with sizes of 0, and then we will grow it in both dimensions until we get to the complete problem. But before we draw the table, The key idea here is that we know how to do base cases. Base cases are easy and trivial. But how can we use base cases or smaller subproblems to build solutions to bigger problems? The idea is that given any item x, you have two possibilities. Either take it or not take it. So either take x or not take x. So this is basically what the 0-1 knapsack problem is. For each item, you're trying to decide whether to take it or not. How does this relate to smaller subproblems? Well, if I have a given capacity, C, if I take x, then this is x, and x has a certain weight. So this is, the weight of x. If I take x, then the space that is left in the knapsack, if the entire capacity is C, this is going to be C minus W of x, right? So if I take x, I will have C minus W of x left in the knapsack. And then, I can fill this with some of the remaining items. Now, deciding or determining, the best subset of other items that I can put here in the remaining capacity is a subproblem that is smaller than the current problem that I'm trying to solve. So the problem that I'm trying to solve is a problem that includes x with capacity of C. Now, if I know the solution to this subproblem, which is the optimal value that I can fit in a knapsack with capacity C minus W of x, the remaining capacity here, and using the other items, okay, then I know what's the best that I can put here, and that's going to give me an optimal solution to this subproblem. Now, this is the option of taking x. The other option is not taking x. If I do not take x, I will just have the entire knapsack available, right? But this is also a smaller subproblem that if I have solved before solving the current problem, I will know the solution to this subproblem. Remember that we will start with the smallest subproblems and we will build solutions to larger problems. So if this is opt2 is the maximum value that I can fit in a knapsack with capacity of C using items other than x. The items other than x, the item that I considered before. Now, how can I determine if taking x is better or worse than not taking x? I'm trying to determine if taking x is good or bad. Well, if I just compare this up to the solution for using the whole capacity and items 1, 2, 3 through x minus 1, I'm assuming that I'm ordering the items in a certain order. And as we will see, it doesn't matter in which order. You can just number the items in any order you want. So considering items 1, 2, 3 through x minus 1, what's the optimal that I can fit in a capacity of C? And using the items 1, 2, 3 through x minus 1, what's the best that I can fit in a capacity of C minus W of x? So I take optimal 2, optimal 1, and add to it what? The value of x. Yeah, not the weight of x, the value of x. So if I take x, I will get this. I will get the value of x because I will take x. Then whatever I can fit in the remaining capacity of the knapsack. That's what I will get if I take x. This is the first option. The second option is if I don't take x, then I will have the whole capacity available, and I will just take the best solution, that take the best subset out of other items that I can fit here. Then I compare these. So if this is, for example, let's put some numbers. If opt1 is 30 and opt2 is 40, and the value of x is 15, then in this case, 30 plus 15 is going to give us 45 compared to 40. Then I much rather take x. Taking x is a bit better deal. But if we change the numbers, what if this what if this was 50 instead of 40? Then in this case, not taking x would be a better deal. So we're trying to choose between taking x and not taking x. Okay. So now with this description, let's now draw the entire table, because dynamic programming is based on a table that has the solutions to all the subproblems. And we will see how this can be put together to construct a solution to the 0-1 knapsack problem. Okay, so my table is going to look like this. Now it's going to be for this example. So I'm going to grow the solution in 2 dimensions. In 1 dimension, I will increase the number of items. In the other direction, I will increase the capacity. So here I have, I think this should be fine. Okay, so the capacity is going to go it's going to go from 0, 1, 2, 3, 4, 5, 6. Of course, it's going to get to the maximum capacity here, which is 8. 7 and 8. Then here I have no items. This is a trivial subproblem in which no items are considered. Here I consider item 1 only. Then here I consider items 1 and 2. And then items 1, 2, and 3. So which square in this table is going to have the solution to the whole problem? Yeah, the last solution. So this is the solution considering all items with a capacity of 8. While, let's look at this, for example, this solution. So this square here will have the optimal solution to the subproblem of considering only items 1 and 2. So item 3 is not considered, only considering items 1 and 2 with a capacity of 4. This is a subproblem. So basically here in this table, we are storing the solutions to all the subproblems to avoid resolving a subproblem multiple times. So each subproblem gets solved once. And because the problem exhibits the optimal substructure, we can use that. We can use solutions to the subproblems to build solutions to the bigger problems. So remember that the 0-1 knapsack problem has the optimal substructure property, but of course it doesn't have the greedy choice property. If it had the greedy choice property, we would have been able to solve it using a greedy algorithm. Remember, to solve a problem using a greedy algorithm, you have to have both optimal substructure and greedy choice property. This problem, the 0-1 knapsack version of the problem, has optimal substructure, and this is something that we will be capitalizing on in building this dynamic programming solution, but it does not have the greedy choice property. Okay, so now by looking at this table, so let's write in general, what each entry in the table means. In general, T of I and j in the table means optimal solution for a knapsack, of capacity j, capacity is j, using items 1, 2 through I. So the entry T of I and j in the table will have the optimal solution for a knapsack with capacity j using items 1, 2 through I. So now this is easy. When you have no items, what will the solution be? 0. So even though this looks like a trivial base case, but we will be able to build on it. We will be able to use it to build solutions to bigger subproblems. Now, when we have item 1 considered, with 0 capacity, what will the solution be? 0, because we will not be able to fit it. So item 1 has a weight of 2, right? Yeah, so it has a weight of 2. And of course, with 1, the value is 0 because we won't be able to fit it. When the capacity is 2, we will be able to fit item 1, and the value of our solution will be 3, which is the value of item 1. Then obviously, will we be able to get something greater than 3 with item 1 only? So in this row, we will not be able to get anything greater than 3, because we are only considering item number 1. This is the subproblem that we are considering. So even if you increase the capacity with only item 1 considered, you're not going to get greater than 3. So it's going to continue 3, 3, 3. Now, we're considering both items 1 and 2. So basically, the new item that we are adding, or that we are considering now, is item 2. Now, when will things start to make a difference? When we get to what capacity? Capacity 5?
No, 3.
3. Because when we get to capacity 3, we will have the option of taking item 2. Before we get to capacity 3, we don't have the option of taking item 2 because it won't fit. So we need at least a capacity of 3 in order to consider item number 2. Before 3, we do not consider item 2. It won't fit. So what we do before we get to 3, we have to stick to the original solution, the solution that we had previously with item 1. So just copy what we have in the previous row. Now, with a capacity of 3, we have the option of taking item 2. But remember, taking item 2 will not necessarily give us a better solution. So we have to compare two options. Take item 2 and don't take item 2. Now, if I take item 2, I will get a value of at least 4, which is the value of item 2. Then I will add to it what? I will add to it whatever I can fit after I take item 2. Now, what will be the remaining capacity at this point? What will be the remaining capacity after I take item 2? 0. Now, with a capacity of 0 and using the items that are the items before item 2, which is in this case only item 1, the solution is here. This is the solution. So I already have it. This is the best solution. This is the best that I can fit in the remaining capacity after I take item 2 using the previous items. So this is going to give me 4 plus 0. Now, if I don't take item 2, what subproblem solution should I look at?
Same as the
Yeah, the previous one, because if I don't take item 2, then I will have the entire capacity of 3, right? And what can I fit in a capacity of 3 using other items? It's this. The answer is I have already computed the answer here. So what I can fit with the capacity of 3 using previous items is this 3. So if I don't take it, I get 3. Which is better now, 4 or 3?
4.
So 4 is better than 3. So I will choose to take item 2. So I will choose to take it and get a 4. Okay, so this is the idea. Now when I get to a capacity of 4, again, I have the option of taking item 2. If I take it, I will get 4 plus what? Plus what I can fit with a capacity of?
1.
Yeah, within a capacity of 1, which is still 0. So it's still 4 plus 0. And if I don't take it, I will still get a 3, because that's the previous solution. And again, 4 is better than 3. Here, if I take it, I will get 4 plus whatever I can fit within a capacity of
2.
Yeah, which is 5 minus 3. A capacity of 5, which is the current capacity, minus 3, because I will lose 3 when I take item 2. So 5 minus 3 is 2, so I will look at this. So it's going to give me 4 plus 3. And the 3 came from this. Okay? So if I take it, I will get 7. If I don't take it, I will get 3. And clearly 7 is better than 3. So I will take it. Then, since I have already taken both items, it's not going to get any better, right? So on this line, on this row, things are not going to get any better than taking both items. Okay. Now the last line is probably the most interesting line, the most interesting row. Now I should keep copying whatever I had on in the previous row until I get to a capacity of
5.
Yeah, capacity of 5. Before 5, taking item 3 is not an option because it won't fit. So just until I get to 5, I just copy whatever I had previously. So I have 0, 0, 3, 4, 4. Now I consider taking item 3. And I have to compare the two options, taken and not taken. Taken will not always be the best choice. So if I take item 3, I will get a value of
6.
I will get a value of 6. But how much remaining capacity will I have? 0. So in 0, I can get 0. Right? So I will look at this. So this is what I can get with a capacity of 0 using the previous item. So I will get a 0. So if I take it, I will get 6 plus 0. If I don't take it, I will get 7. So which is better? 7, which means don't take it. So now I just take the 7, and I will not take item 3. Now when my capacity becomes 6, again my options are 6 plus what I can fit within a capacity of 1, which is a 0. So if I take it, I will have 1 more kilogram that I can take. But with 1 more kilogram, I can fit 0 of the previous item. So it's going to still be 6 plus 0 compared to 7. And 7 is going to win again. But here, I will have 6 plus a remaining capacity of, what's the remaining capacity here? 2. So with the remaining capacity of 2, I look at this square with the remaining capacity. So it tells me that with the remaining capacity of 2, you can fit a value of 3. So then I can get 6 plus 3. And 6 plus 3 is better than 7. So now I take it and get a 9. And here, it's 6 plus what I can fit with the capacity within a capacity of 8 minus 5, which is 3. So I can fit 4. So this is 6 plus 4, which is 10. And 10 is better than 7. Okay? So this is the this is the dynamic programming algorithm. Okay? And obviously my solution is going to be in the last square. But this square tells me the value of the solution. It doesn't tell me which items have been taken and which items have not been taken. So how will I know which items have been taken and which items have not been taken? Okay, so when I look at this square, does it tell me whether item 3 has been taken or not? If I compare it with the surrounding squares, will I get a clue whether item 3 has been taken or not? So what happens when you take the item? When you take the item, the value in the current row will be different from the items in the value in the previous row. When you choose not to take the item, like we did here, when we did not take the item, we just, the same value, the value in the current row was the same as the value in the previous row. So by comparing the value in the current row with the value in the previous row, we can tell whether the current item has been taken or not. And in this case, because 10 is different from 7, then I know that item 3 has been taken. But then I have to decide about other items. So now to which square should I go? So this solution is based on which square? For the, for which solution? For the remaining items, items 1 and 2. So I have to go to which square?
Capacity for item 1 and 2.
Yeah, it's based on the remaining capacity. So the remaining capacity is 8 minus the weight of item 3, 8 minus 5, and that's 3. So I go to the previous row and column 3, which is this. So now I go to this. Now I do the same thing. Did I take item 2 or not? I compare it with the previous row. And this tells me that the values are different, so I have taken item 2. Okay? So item 2 has been taken. Then I go to which square? 3 minus 3. Right. 3 minus 3 is 0, so this will put me here. Now I compare 0 with 0, same value. So I did not take item 1. Okay? And then since I'm at item 1, that's it. So by tracing back, I can decide which whether a certain item has been taken or not. Okay, so let's now write the pseudocode for this dynamic programming algorithm. So it's gonna be dynamic programming 0, 1 knapsack. And then I get W, V, and N, and C. And these have the usual meanings. So what's V? V is an array of values. W is an array of weights. N is the number of items. And C is the capacity. Okay. So now this algorithm is just going to construct this table. So first, create a two-dimensional 2D array with what's the number of rows?
Number of items.
Plus 1, right? Because you have a no item row. So with n plus 1 rows and c plus 1 columns.
What do we call that?
I'm sorry?
What do we call that array? Is that T?
Okay, yeah, a two-dimensional array T. Yes. T for table. Then we will fill the first row with zeros. So all what we do for j equals 0 to c, t of 0 and j equals what? T of 0 and j equals 0. So this is fill the first row with zeros. Then I will start filling the rows from 1 to n. For I equals 1 to n, now for I equals 1 to n, and for j equals 0, right? For j equals 0 to c. So I goes from 1 to n, and j goes from 0 to c. Now I have two cases. Remember that first I had to determine whether the item is an option or not. So if the item is not an option, I will just, I will not have to compare taking against not taking. So if the item is not an option, how do I detect that? If what? If the item doesn't fit.
Weight is greater than capacity.
If the weight of I or j,
J.
no, I, see, I is the item number, right? So let's put a comment here. I is the item number, J is what?
Capacity.
Capacity. The column is the capacity. So if weight of I, if the weight of I is greater than what? The capacity. So what's the capacity at that point? T of
A comma J.
J. Sorry, the value J itself. J is the capacity. If the weight of I is greater than the capacity J, right, then the item doesn't fit. So this means that item does not fit. So if it doesn't fit, I will just take the previous solution. And the previous solution, it means that T of I and J equals
T of I J minus 1.
J minus 1 or I minus 1. When I go one row up,
I minus 1.
I minus 1. I is the row number. So it's going to be T of I minus 1 and J. Take the solution from the previous row. Take solution from previous row. Why take from previous row? Because the current item doesn't fit, so it's not an option. So this is the less interesting case. The more interesting case is the else. If it fits, then my T of I and J is going to be the maximum of T of I and J is the maximum of the take and the not take. Now what's the take? What's going to be the value if I take it? If I take it, then I will have its value. What is its value? V of I. Its value is V of I plus what I can fit in the remaining capacity. Now how do I express the best that I can fit in the remaining capacity? How do I express that? It's going to be T of something in the table. T of, is it in the current row or previous row? Previous row, which means I minus 1. Now what's the column number?
J minus the weight.
Yeah, exactly. J minus the weight of I. J minus the weight of I. Okay? So this is basically, this is the remaining capacity. This thing here, this is the remaining capacity. This is the remaining capacity. And if I don't take it, so this is take I. So this thing is take I. Now if I don't take I, what's the option? What would be the value? T of the previous row. What is the previous row? T of I minus 1 and what J? Did we change the column? No, when you look at the previous solution, it's previous row, same column. So previous row, same column is this. So we're taking the max of take and not take. So this is don't take. Okay, so this is the algorithm. Okay, so basically you go through the items. So first set the first row to 0. The second, for rows 1 through n, you go from j equals 0 to c. If w of I is greater than j, just take the previous value, which is T of I minus 1 and j. If the item fits, then you have two options. Take it or not take it. So you compute the value for taking it, and the value for not taking it, and get the bigger value. So in order to get the value for taking it, you have its value plus the best that you can fit within the remaining capacity. This is the remaining capacity, and this is the previous row using the previous items. And this is what you can fit if you don't take it. So obviously here you have a bigger capacity, the whole j. Here you have j minus the weight of the item. Okay? All right, so this is the algorithm for building the table, but what's the algorithm for identifying the items that have been taken? So let's write it here. It's going to be an easier algorithm. So we started from so let's call it find items or decide items. So the decide items, we start from I equals n and j equals c. I equals n, the last square. And we go for I equals n to 1, or down to 1, to emphasize that we're going down. If what? How did we decide if an item is taken or not?
Comparing with the
If t of I and j is what?
Greater than
Is greater than
u5 minus 1j.
t of previous row, same j, is greater than the value in the previous row, then take item I. Take item I. And when I take item I have to go to this square. So how did I decide what this square is? I changed j. J equals j minus
Weight of I.
weight of I. And in fact, that's all what I need. That's it. And I will get decremented automatically because it's the loop counter. So I'm starting from n all the way to 1. So each time I go one row up, I may change the column. I change the column if the item is taken, but if the item is not taken, I do not change the column. Okay, so this is the algorithm. Now what's the running time of this thing?
NC.
N squared?
NC.
Yeah, nc. So this is n and this is c. So the running time here, t of n, is theta of nc. And what's the running time of this thing? This is theta of n. This is easy. This is just theta of n. This is theta of nc. Okay. Any questions so far? Yeah.
If the weights are in decimal value, what do we take as the columns?
What do we take for the columns?
Yeah, I mean, if the weights have decimal values, like it can be 2.002 kg, then we would need to take all the decimal places in this column.
Yeah, here you will have to cover all the weights, all possible weights, whether they are integers or fractions. But if they are fractions, you can find a the smallest common factor, or a number that an integer. For example, if you have halves, right? So you multiply by 2. If If you have thirds, you multiply by 3. But the idea here is that you will have to cover all possible weights and all possible combinations of weights, all the possible weights that you can have for the knapsack. Okay, so now, so there are a couple of things. In fact, a couple of important points. First point is, what proves the correctness of this? Where's the proof of correctness here? So here the proof of correctness, yeah.
This is the fact that we solved every possible combination.
In fact, we did not solve all possible combination. If we solve all possible combination, we will get an exponential, an algorithm that is exponential in the number of items. So we did not look at all possible subsets of items. We looked at all possible subproblems, not all combinations. So these are two different things. Combinations are subsets of items, and the number of subsets of items is exponential, which is the power set. But we looked at all possible subproblems. But that alone doesn't prove that this is correct. The proof of correctness here is implicit in the way dynamic programming works. In fact, there is an implicit inductive proof here. Recall that for induction, to prove something by induction, you have to have a base case, and then you have to prove that if this theorem is true for n, it's true for n plus 1. So you have to prove the continuation or the induction. So you just prove a trivial base case, then you prove that if it's true for n, it's true for n plus 1 or for larger values. And this is exactly what we are doing here. So we are starting with a trivial base case that is clearly true, for which clearly if we have no items, then the value is going to be 0. So this is our base. This is our trivial base. But then our inductive step is these equations. These are in fact recurrences. Recurrences in the sense that they define the value for I and j in terms of smaller i's and j's. Yeah. So the value of this square for this I and j is defined in terms of this square. So in fact, the correctness of this follows from the correctness of this equation. So this equation is saying, okay, if it doesn't fit, I will have to take the previous solution. That's clear. Here, if it fits, I have only two options, take it or not take it. And I'm considering these two options, take or not take, and I'm looking at the value of take and the value of not take, and taking the value that is larger, the larger of the two, take and not take. Okay? So here the proof is implicit. The proof is implicit in these equations that I'm using. But it's an implicit inductive proof. So induction is used a lot in proving the correctness of algorithms. Because in algorithms, we tend to repeat things. But see, this is a different kind of repetition compared to what we were doing in greedy algorithms. In greedy algorithms, we were taking a top-down approach. We were making a decision, making the greedy choice. Then, with the greedy choice, we were left with a smaller subproblem, and then solving the smaller subproblem. So in greedy, we were starting with a big problem and making it smaller. Here, we are starting with smaller problems, and building solutions to bigger problems. Okay, so this addresses the correctness. Now, one important subtlety here is the question of whether this is polynomial or not. Is this polynomial In fact, surprisingly, the answer is no. So this looks polynomial, but indeed it's not polynomial. Why isn't it polynomial? So in order to understand why this is not polynomial, we have to think carefully about the input size. So let me try to explain this. Now, we have to think carefully about the input size as opposed to the magnitude of the input. What do I mean? Now, think of an input file that has the input to an instance, an input that represents an instance of the 0-1 knapsack problem. So that input file will have n, for example, 1,000. N is 1,000, and C is probably 10,000. Or yeah, let's do it the other way around. So it doesn't matter, in fact. So this is, let's say that this is C, this is N, and then if N is 10,000, we should have the weights and values of 10,000 items. So we will have, weight 1, value 1, weight 2, value 2, weight 3, value 3, until we get to weight 10,000, value 10,000. Think about the size of this input file. Now, what is the asymptotic complexity of an algorithm? The asymptotic complexity of an algorithm is a mathematical relation between the number of times or the number of operations and the input size. Now, in terms of input size, for n, you will have n lines in the input file. So in fact, the relation between this and this is polynomial. It's even linear, or even so it's at worst linear, because I have n items, so I have a big input, and this is n. But the relation between C and this relation is not linear. Why? Because if you look at the size of this input, not the magnitude of this. Now, the magnitude of this is 1,000, right? But what's the size of it in terms of the number of characters? How many characters do we have? 4. I have 4 characters. And with 4 characters, I got C. So with 4 characters, if we point it to this loop is executing C times. Well, in fact, yeah. In fact, I should point these to the loops. It will be clearer. So this goes to this loop, and this goes to this loop. So the asymptotic, you can think of the asymptotic complexity of an algorithm as an amplification factor. To what extent it takes a small input and amplifies that or magnifies that and does a lot of computation for such a small input. So if an algorithm does a lot of computation for a small input, it's a complex algorithm. If it doesn't do a lot of computation for the size of the input, then it's not complex. So here, for only 4 characters, we ended up executing this loop 1,000 times. While here, for 10,000 lines, we executed the loop 10,000 times. So this relation is obviously linear. We do not have a big amplification factor, but here we have a big amplification factor because this is just a number. So if you look at this relation, if you draw a table like this, the value of C, and here input size, and here loop iterations. If you look at this, if the value of C is 100, the input size is just 3 characters. 1, 2, 3. And the loop is going to execute 100 times. If the value of C is 1,000, then the input size is what? 4 characters, and the loop is going to execute 1,000 times. If the value of C is 10,000, then the input size is going to be 5, and the loop is going to execute 10,000. Now, the complexity of an algorithm is the number of operations, which is here measured by the number of iterations of the loop, as a function of input size. So if you plot this column, the numbers in this column versus the numbers on this column, what kind of function will you get? This is an exponential function. It's an exponential function because, you know, it's basically this is, you know, it's 100 is 10 power 2, and 1,000 is 10 power 3, and this is 10 power 4. So basically the relation here is 10 power n minus 1. So it's exponential. So this is a hidden exponential relation. And the cause of this is that this input is just a number. And our input size is not the magnitude of the number. Our input size is the number of characters that encode the input. So think of, you know, the input size is this, which is the number of characters that encode the input, as opposed to the magnitude of the input. Now, this doesn't apply to n, because with n, the input is not just a number. We have an actual list of n items. So here the input is so big, the input size is big. And this does not amplify this. While this loop, the number of iterations of the loop, is a big amplification of such a small input size. It's exponential, in fact. Okay? So that's why this solution technically is not a polynomial time solution. This is an exponential solution. But in practice, from a practical point of view, this algorithm will behave like a polynomial time algorithm most of the time. It will behave like a polynomial time algorithm as long as C is not huge. As long as C is reasonable, this algorithm is going to behave like a polynomial time algorithm. So strictly speaking, mathematically speaking, this is an exponential algorithm. It's exponential in the input size. But from a practical point of view, it's practically polynomial. In fact, it's referred to as pseudo-polynomial. So this is considered a pseudo-polynomial algorithm. Pseudo-polynomial. And as we will see when we talk about NP completeness, the 0-1 knapsack problem is an NP complete problem. But because it has a pseudo-polynomial time algorithm, it's a weakly NP complete problem. So it's not strongly NP complete. It's weakly NP complete because it has this algorithm that is mathematically exponential but practically polynomial.